can see who wants to get 2 out of it, but that's not my problem.
Yeah, exactly. Right, you saw. I was like, I actually also thought about moving ones.
All right, so let's get started. This is a tough spot after lunch, so hopefully I'll be able to keep you awake. Okay, let me start recapping what I discussed yesterday. So we were trying to understand how these general principles, symmetry, locality, unitarity, causality, constraint scattering amplitudes. So we said that, okay, just based on symmetry considerations, we found that amplitudes, they conserve momentum. They were a function of these angle and square brackets that I will review in a second. These contractions of these spinor helicity variables corresponding to each particle, maybe a bunch of couplings, maybe some UV scale physics beyond what we can describe. And these things have some prescribed little group transformation properties. Okay, so if they were massless, there was some homogeneity. If they were massive, they had to carry some representation of the little group. Okay, so today we'll do mostly massless stuff. And then we said that locality unitarity tell you that this amplitude, okay, it has to have some poles somewhere, and also some branch cuts, some logarithms, but fortunately the coefficients of the residues on the pole and the coefficient of the log, they are fixed in terms of amplitudes themselves. Okay, they're fixed by unitarity. And then causality tells us that, okay, this is actually a function of complex momenta, and there was this property of crossing that relates different processes. Okay, so today we're going to descend from this kind of high world of general principles to the dirtier but also more fun world of calculations. And we're actually going to try to put these principles to work and actually compute some amplitudes. But first, let me just get some kinematics out of the way and some notation so we can actually write these amplitudes. So let me just remind you that these brackets ij, they were just some contraction of these spinors corresponding to each particle. And in particular, because this is an antisymmetric tensor, these are antisymmetric. Okay, and in particular, this is 0, similarly for the square brackets. Okay, so angle bracket II or JJ is 0, and same for square bracket. Okay, so another way to think about this, guys, is so this spinor helicity they're actually solutions to the massless Weil spinor equation, wave equation. Okay? So if we have some equation of motion, which is something like this, some derivative of a left-handed Weil spinor. So this is the equation of motion. If we go to momentum space, we just do the Fourier transform of this guy. Let me call the Fourier transform of this guy lambda tilde. Then this equation, this is going to turn into some momentum. So it's just going to turn into P alpha alpha dot of lambda tilde alpha dot. Right, let's say this is particle 1. And actually, if I write this in terms of the spinors, this is nothing else than lambda 1 alpha, and then angle bracket 1, 1, which is 0, by the antisymmetry that we just described. Okay, so actually, this is basically a solution to the free wave equation for massless spinor.
A square bracket there? Is that intentional?
Yeah, because it's a contraction of 2 lambda tilde spinors. Right, so P is lambda 1 alpha tilde, alpha dot tilde, right? And then these indices are contracted, which is with this thing, well, it's the dotted version of this, and this is antisymmetric, so it's 0. Yeah. So essentially, the usual wave functions for spinors, U, W, U bar, W bar, that you're familiar from when you do calculations with your X spinors from your textbook, they all can be rewritten in terms of this guy. So this, apart from the momenta, they're just the wave functions of your favorite fermions. Okay. Another thing is that this combination, if you calculate the following combination, you can show that this is simply the inner product of these two guys, also known as the Sij Mendelssohn variable, okay, because these are massless. So it's Pi plus Pj squared. And this means that this guy is basically square root of the absolute value of Sij times case, and the angle bracket is just the complex conjugate. And this phase changes basically if you rotate particles ij around their average momentum. Okay, so just to get some more intuition about what this is, in particular, this thing has dimensions of energy, because Sij has dimensions of energy squared. So,
Use the e to the negative.
Sorry. Yeah. Okay. And then 2 more things. So there's an identity that this thing satisfies called the Schouten identity. Which is the following. Lambda I jk plus lambda j ki this is 0 for any value of alpha, so you can contract this with a 4th spinor, and this is always going to be 0, and this is just a statement that these guys are 2 by 2. These are 2-component vectors, 2-component spinors, so there's only 2 of them that are linearly independent. Okay, so there's always going to be some linear dependency between any 3 of these spinors. So, okay, so an exercise, prove this. It's actually very easy. And then the last thing is, how does momentum conservation look in this language? So momentum conservation is basically the statement that if we contract, if we write something like A, okay, let me actually, before this, introduce one more piece of notation, which will make our life easier. Consider the following thing, Ij jk. So what is this? It's going to be something like I alpha j alpha But this thing here is just pj. So usually we use the following notation. Or equivalently, k, j, I, just to save a little bit of chalk. So in this language, momentum conservation it just looks like this. Pick any pair of spinors A and B. You can insert here like the full momentum, so sum over I, pi. And then you can just write that as sum over I, A, I, IB equals 0. Okay, so there's some relation between these guys, just from momentum conservation. Is the notation clear? Yeah.
Sorry, we have the same properties for the square brackets, right?
For the square, so yeah, here, yes. There's a similar identity for the square brackets. Momentum conservation mixes both kinds. But the Schouten identity, you have this linear relation between either tilted or untilted spinors. Yeah. More questions? Yes. Which, yeah, this depends on p squared equals 0, because Sij typically is pi plus pj squared. Yeah, but even for the massive case, you can find that something like this holds. So today I'll mostly be talking about the massless case because it's simpler. All of this is the same. Like, it doesn't matter whether they're massive or massless. Yeah. If they're massive, you can add an extra index here, but the same thing will hold. Yeah. Because again, like you can only have 3 of them. It's exactly the same. It just means that there's only 2 linearly independent spinors, because these are 2 by 2. These are 2 component objects. Right? We can choose a basis of 2, and we can decompose any other guy in this basis. Yeah. More questions? OK. So finally, we can write some amplitudes. Let me go here. So since we said that the coefficients of these poles and logs, they're fixed in terms of simpler amplitudes, let's start with the simplest kind of amplitude that we can imagine, which is a 3-point amplitude, and a 3-point amplitude for massless particles. Okay. Okay, so this might sound a bit funny, because perhaps you remember that if you try to satisfy both energy and momentum conservation for massless particles at 3 points, there is no solution. There's actually a solution for complex kinematics. Okay, so if I make the momenta complex, then there's actually an object that I can write. So there's some special kinematics that will make our life hard and easy. So we have the total momentum. I'm going to write as lambda 1, lambda tilde 1, plus lambda 2, lambda tilde 2, plus lambda 3, lambda tilde 3. This has to be equal to 0. Okay, so now let me contract this with a lambda 1, okay, with one of the free indices, right? So basically, if I contract lambda 1 alpha with this p alpha alpha dot, the first term, because of the antisymmetry, is going to die, right? So I'm going to have that the first term is 1, 1, which is 0, plus 1, 2, lambda 2 tilde, plus 1, 3, lambda 2 tilde. So what are the solutions to this equation? There's only 2 options. So we can have either lambda 2 is proportional to lambda 3. And actually, if you do the same exercise with another guy, you would find that all the lambda tildes are proportional. So lambda 1 tilde is proportional to lambda 2 tilde, proportional to lambda 3 tilde. Or these things are 0. And these things are 0. In order for this guy to be 0, the only way it can be 0 is if 2 is proportional to 1 again. because this is linear. This is just a contraction of lambda1 and lambda2. Okay, so the only way it can be 0 is by antisymmetry if they're proportional. So the other solution is that lambda1 is proportional to lambda2 is proportional to lambda3. Okay, so if we choose this, that means that all angle brackets are 0. And if we choose this, that means that all, square brackets are 0, and this is all angle brackets are 0. Okay, so we can only write amplitudes that have either square brackets or angle brackets. In particular, if we consider any Mandelstam, so pi.pj, I just told you that this thing is ij, and because either the square brackets or the angle brackets are 0, all of these are 0 at 3 points. So it cannot depend explicitly on momenta. 3-point amplitudes can only depend either on these guys or these guys. Okay. So there's two options. I have either this depends on ij, and there's only one thing that I can write. I can just write g 1, 2 to some power, 2, 3 to some power, 3, 1 to some power. And this has to be a constant, because there's nothing else it can depend on. Okay? Or the same thing with okay, I haven't even told you what kind of particles I'm scattering, anything, but just based on this simple kinematical argument, we have written the most general formula for any massless particle, any massless 3-point amplitude. Okay? Yes?
How do we know it's a monomial and that we don't have to like add other terms?
What other terms?
I mean, with like different AB.
Okay, yeah, okay. So that's going to come next. So what we haven't used yet is the fact that now we have to choose what is the helicity of each particle. So that's going to tell you that actually these powers will be fixed in terms of the helicity. Okay, so in principle, yeah, you could write some JABC, some sum over these things, but we'll see that you can only have one of the monomials for a given helicity. Okay, so let's do an example. Sorry? What is this? Lambda 1. This is 1, 2, 2, 3, 3, 1. Here? This is proportional too. Yeah. This is ij equals 0. So any pair of this, any contraction of these guys will be 0 because they're proportional. This? I'm missing lambda. Oh, yeah, sorry. That's right. Thank you. Yeah. Okay. Someone's paying attention. Yes.
Where do we use that it's massless?
We use that it's massless when first of all, we just wrote this one spinner per each momentum. So we actually wrote this thing as just lambda 1, lambda 1. Yeah.
Sorry.
Yeah.
How we can see that it's a complex solution?
Well, because of this. Because for real momenta, right? If each one of these momenta is lambda 1 tilde. So if the momenta is real, they have to be related by complex conjugation. So you see, for real momenta, we have to have either like both of these things at the same time. Okay, so the only solution is that everything is 0. It's only if you allow the lambdas and lambda tildes to be independent, which is only true for complex momenta, that actually I can write a formula that depends either on the square brackets or on the angle brackets. Okay, thanks. Great question.
So are the tilde lambdas, are those just the complex conjugate of the non-tilde ones?
For real momenta.
What do
Yeah, for complex momenta, they're just independent variables. Yeah. Okay, more questions. So let's get started with the examples. Actually, many of the examples I'm going to describe are for gravity amplitudes. So this might seem a bit exotic, but there's a couple reasons why I want to do that. First of all, because actually it's a hot topic right now in amplitude, because we're able to use this to do certain computations of gravitational wave physics. But also because you'll see that these methods that we use, they actually shine when you try to compute gravity amplitude, because I don't know if you've tried to compute anything perturbatively in gravity, but okay, if you just work out the Feynman rules for gravity, then there's an infinite number of vertices, okay? And each one of these vertices is a nightmare. So actually, I'm going to issue a challenge. So at some point, I'm going to write down some like gravitational Compton amplitude. If anyone can compute it, even with your computer, before the end of the day, I'll buy you dinner, okay? But you have to do it using like the usual methods, like Feynman rules and all of that, okay? It's not impossible, but okay. But we'll just write the answer in a few minutes. Okay.
And this also works for a non-perturbative.
Yeah. So this statement about 3-point amplitudes is completely non-perturbative. Yeah.
Can I see G as coupling?
It's just a coupling. Yeah. Yeah, so these 3-point amplitudes are extremely constrained. They're also not very physical because they're only for complex momenta, but yeah. But we'll see that they're the building blocks that we need. Okay, so let's compute the free graviton amplitude. Okay, so let's choose the following helicities. Let me choose the helicities where the graviton has -2, second particle has -2, the third one has +2. So helicity 2, massless helicity 2, that's a graviton, right? And then the little group tells me that this thing needs to transform as T1 to the 4, where T1 is the variable that I'm scaling the first spinor by, T2 to the 4, and then T3 to the -4. So I just scaled independently each one of the angles and tilted and untilted spinors. In this case, there will only be one of them. And this is the specified homogeneity from the little group. Okay. Okay, so if you just scale that amplitude over there, then you'll find the following equations. A plus C equals 4, because only the first and the last amplitude have the angle 1. So I'm scaling the first spinor. So I just pick a weight that goes like A plus C. And then for T2, I will get A plus B equals 4, B plus C equals -4. And if you solve these equations, there's only one solution, and we find that this amplitude is simply some constant, let me call it kappa, 1, 2 to the 6, 1, 2 squared, 3, 1 squared. Okay? So we already computed the free graviton amplitude just based on this little group scale. Okay? Okay, you can try to compute the, sorry?
One of those be 2, 3.
Yeah. Thank you. Okay, and this kappa, this thing has dimensions -1. So actually, this is some non-normalizable theory, right? So this is basically 1 over this UV scale, which in this case would be M Planck, because it's a gravitational coupling, or also it's basically like square root of 8 pi g, if you write it in terms of the usual Newton's constant. Okay, notice something here, that this thing has a complex pole, has this pole somewhere in the complex plane for this angle. So when one of these guys becomes 0, then this thing is going to blow up. And this will be important in a second. Okay. Let's see, but there's other amplitudes for 3 gravitons. So let's choose a different helicity configuration. So let's look at 1, -2, now you can do the same exercise, but I'm just going to write it down, and you see immediately why this is the answer. This is going to be some alpha, 1, 2 squared, 2, 3 squared, 3, 1 squared, because then all of these have to scale like t to the 4. So if I scale here 1, it scales to the 4th power. If I scale 2, it scales to the 4th power. Same for 3. Okay. So what is this coupling here? It turns out that this coupling, notice that this has higher dimension, right? This actually will go like 1 over lambda uv to the 5 just by dimension analysis, because each one of these brackets has dimensions of energy. So this is energy to the 6, right? And amplitudes have dimension n, 4 minus n. Right? So the amplitude has to have dimension 1, just mass dimension 1. This is 6, this has to be minus 5. So this is something which is higher, it's suppressed by some higher power of the UV cutoff. And actually you can check that this is the amplitude you would get if you add some r cubed term to your Lagrangian. Okay, so this is an independent amplitude, and there's an independent coupling, and here we just see that they appear when we look at different helicity configurations. You might ask, which r cubed? I can imagine that there's different r cubed combinations that I can write. Actually, there's only one independent amplitude, because amplitudes are invariant under Filter definitions and integration by parts. So even though you can write many different r cubed operators, if you mod out by Filter definitions and integration by parts, you will find a single independent r cube operator, which is this one. Okay, so I'll comment more on that later. So this is one of the advantages of computing directly amplitudes rather than trying to classify operators in a Lagrangian, especially in complicated theories like gravity. Yes?
Yeah, so besides the constant, in which point are you using that it's a graviton and not a gluon?
When I use the fact that, so remember, the rule, I didn't write it explicitly today, but the rule is that in every time I scale the spinors, right, the amplitude needs to go like -2 times the helicity. So the fact that here I said that the power here has to be 4, it's because I specified that the helicity has to be 2. So that's where I said that it's a graviton, not a gluon. But you can do the same for a gluon, and you'll see that the answer is very simple, right? It's just going to be half of each one of these powers, right? So actually, this 3-point amplitude for graviton is just the square of the 3-point amplitude for gluons. Okay? And I'll give you an exercise later about the gluons.
That's the double cup.
Yeah, that's right. Yeah. Okay. Where am I? Let me erase this. Okay, let me give you an exercise. So this is not gravitational. So consider the amplitude for 2 massless fermions. So helicity 1/2 or -1/2, and 1 photon. So massless vector, which is helicity 1, right? So something like this. And then show that there's 2 independent amplitudes up to parity. You can work out what these amplitudes is, and actually you will see that this amplitude, the coefficient, is precisely the electric charge. And then there's another independent amplitude that you'll see that has slightly different dimensions, and this thing is basically the magnetic moment of this fermion. Okay. Again, playing the same games, just imposing the little group weight, we can write directly the answer, and there's some coupling that here we can interpret as such. Okay, any questions so far? I'm going to compute one more 3-point amplitude because we'll use it later. Yes?
You can't play this game with the 0.
You can play this game, and actually you will find that because you cannot have any momenta, right? Any sum over momenta are 0. So you will find that there's only one independent amplitude, which is a constant, and that's actually true. Like if you write any term that looks like phi and then like any number of derivatives this thing, that always can be field redefined away. There's no amplitude of 3 scalars with derivatives. Okay? There's only a phi cubed interaction. So actually, that's a good exercise to check that. So basically, what will happen is that here, whenever you see like this momenta you will get, it will always be some product of momenta, and it's going to be 0 by kinematics in 3D. Yeah. But you can see that this is much more powerful for particles with spin or helicity. OK, so the last one that I want to compute is a 2-scalar actually massive scalar and then 1 graviton. And here we see a problem, which is that if we want to write something that doesn't have any weight on the scalars, right? So this is an amplitude that looks like this. So I have 1, 2, 3, and this has, say, +2 helicity. I'm not allowed to write anything that has weight in these guys, but then if I only write spinors of 3, then I just have 1. So I cannot contract it with itself because that would be 0. So what do we do? It seems that there's some tension here. We cannot write anything down. Actually, we can. So let's think about the following object. So let me just contract the momentum of this particle. So P1 alpha dot with the spinor corresponding to the graviton. Now this thing, actually you can show that because when I contract with lambda 3, I would just get P1 dot P3. That will be 0 for similar reasons. Then this has to be proportional to lambda 3. And now you see that this thing is interesting because this object here has some spinor weight. Okay? So there's some proportionality constant that for this equation to be compatible, right, it has to have like spinor weight 2. So let's extract it by just contracting this with some auxiliary spinor, some random spinor that I've chosen. Yes?
Sorry, when you talk about like having weight, what do you mean?
That it scales when I rescale by this t factor. Yeah. Yeah. Sorry. The question is, what do I mean by weight, by little group weight? And I mean that this thing transforms under the little group with some power, so it will rescale by some power of t. Yes.
So in that example question, the Julio is massless.
Yes. OK, so let me write x by contracting with an auxiliary spinor, which I'll call eta. Okay, so I just contracted this with eta. On this side, I just have angle eta P1 angle square 3, which is the numerator. On the right-hand side, I just have angle eta 3. So I can move this to the left-hand side, and I write x. And you see that indeed it scales with when I rescale 3 yeah, when I rescale the 3 spinors. Okay, so I see that x will transform as t to the minus 2x when I scale 3. Okay, what is this weird object? Okay, and sorry, the last thing I wanted to say is that then this amplitude I can write just as some kappa prime times x squared, right? Because this thing now, if I want this to be helicity plus 2, it has to scale like t to the minus 4, and this will do the job. But what is this weird x object? Let me leave it here. You're actually familiar with this. So this x, I can write it epsilon dot p1, or this epsilon plus alpha alpha dot, it's the same. It's what we usually call a polarization vector. Okay? And this polarization vector is this weird thing that we need to introduce to write this 3-point amplitude. So we see that, okay, we have some arbitrary spinner here. And what happens if I rescale this spinner, if I choose a different one, right? So if I rescale it, this doesn't change, right? So let me write a linear combination of this and this, because any other spinner, I can write a linear combination of these two. And I will see that if I change eta to some a plus b lambda 3, then actually you can easily see that this object will shift precisely by the momentum of 3. And we know that that's actually how a polarization vector should behave. It's only defined up to its longitudinal part. Okay? So this is the only place where kind of some gauge redundancy is going to appear in my lectures. Okay? It's only when I try to write this 3-point amplitude, there's this funky object that I need to introduce. I need to introduce some auxiliary spinner. The answer doesn't depend on it, right? Because if I shift epsilon by P3, I told you that all the products are 0. So actually, this x is by the choice of the spinner. But if I want to write it explicitly, I need to choose some reference. Okay? And that choice is basically like a gauge choice. OK, any questions about this? Now, the nice thing is that now we're going to start writing 4-point amplitudes, and we'll see that these guys will disappear completely. So I'll never see this polarization again. We'll be able to write everything just in terms of the spinners of the particles that are involved in the process without any auxiliary anything. So this is the last time you'll see a polarization. OK, questions before I move on to 4-point amplitudes? OK, so just to summarize, 3-point amplitudes are extremely constrained. They only make sense for complex momenta, but basically they're completely fixed by these little group properties, which are basically symmetry and dimensional analysis. And we can read off the different coefficients and match them with operators in a Lagrangian if we wanted, but we can just write down the answer directly like we do when we do dimensional analysis. Is everyone sleeping? OK, 4-point amplitudes are more fun because we have more variables. Right? There's these Mandelstam variables. There's S equals P1 plus P2 squared, T is P1 plus P4 squared, and U equals P1 plus P3 squared. And now these things are not 0 at 4 points. There's going to be some relation between these because of momentum conservation that I'll review. So if all the particles were massless, it will be S plus T plus U equals 0, which basically follows from momentum conservation. But OK, let's just start writing amplitudes in terms of these variables. And again, I'm going to write a gravitational amplitude. So this is the one that, if you can compute before the end of the day, you get 3 dinner. And if you compute it by hand, you get 3 dinner for the rest of the week. Yeah, it's a pretty safe bet. OK, so I have 2 massive scalars, and then 2 gravitons. So it's like a gravitational Compton amplitude. OK, so we need to write something, some factor that scales in the right way under the little group transformations of 2 and 3, and that's the scale when we write it in terms of 1 and 4. So I can just make a choice. So let me make a choice. 2, P1, 3 to the 4th. And this scales properly because when I scale lambda 2, this scales like 2 to the 4th, which is what I should have for a -2 helicity particle. And if I scale lambda 3 tilde, which scales with t to the -1, I get -4, which is what I should have for a positive helicity particle. Okay? And then everything that is left is some function of these Mandelstams. And for this process, momentum conservation, you can check that it tells you that s minus m squared plus u minus m squared plus t equals 0. So actually, I can just make a choice of 2 of this. In principle, these would just depend on 2 variables, s and u. And actually, just by both symmetry of these particles, we can see that this function f as u has to be symmetric under the exchange of these 2 variables. Actually, this is also true as a crossing relation. It will be true that if I cross this amplitude to get the scattering of the antiparticles, there will be a relation like this. OK, so we're trying to constrain the answer. See what else we know. So this thing here, remember, each one of these spinors have dimensions of energy. This has dimensions of energy, right? So this is energy to the 4th, right? So the dimension of this thing here is m to the 8th. And a 4-point amplitude in 4 dimensions needs to be dimensionless. So this function here, its dimension is to be -8. So whatever we write needs to have the right dimensions. And what else do we know about this function? So we already exhausted the constraint symmetry that tell us what is this little group factor. We know it has to have some poles, right? Because we constructed these 3-point amplitudes, the one that I just erased, for 3 gravitons. So we had both a 3 graviton amplitude and a 2 scalar 1 graviton amplitude. So this amplitude has to contain some poles. When t goes to 0, when s goes to m squared, and when u goes to minus m squared. So when s goes to m squared, the pole will correspond to the following so-called factorization channel. So it's a process where 1 and 2 scatter. There's some other particle p that goes through. And I have 3 and 4. Similarly, when I take u on shell, then I'm going to have the same thing, but with 3 and 2 exchanged. And then the final pole, when t goes to 0, should look something like this, where I have a 3 graviton amplitude here, and then here just the scalars. And notice that here you could have both helicities crossing by unitarity. So we'll come back to that. OK, so we need to write something that has all of these poles. And we're only allowed to have single poles in the amplitude. So just by dimensional analysis, plus this fact that I'm only allowed to have single poles in one of these things, it's pretty easy to convince yourself that the only solution will be something like this. Some coefficient beta over s minus m squared, u minus m squared t, right? Where this thing has dimensions of 1 over energy squared. And these have each one dimensions of energy squared. So this has the right dimensional analysis properties. And we'll see that we're going to check factorization now and see that this is actually the only thing that is consistent. So if you wrote any other combination that has poles, you will see that unitarity would fail. Okay? So it's this plus some unspecified function. And actually, I'm just going to write polynomials. Okay, so from now on, and I'll comment about this a bit more later, but I'm just going to care about the expansion of the amplitude for energies which are much less than this UV scale. So actually, let me write this explicitly. This is where we're run into some trouble, and we need to think about as an effective field theorist, and we need to exploit the fact that we have a separation of scales, and we're going to assume that we can only describe the amplitude for energies which are much lower than this lambda UV. Okay, so okay, it has to have this pole. In general, it could have some other crazy stuff, but at low enough energies, we can always expand in inverse powers of 1 over this lambda UV.
Is there a way to bootstrap the special functions then in the full answer?
Not analytically. There's some, oh, sorry, yeah. Is there no way to bootstrap just the full answer in some way using these principles? Not analytically, there's some numerical approaches that maybe I'll have to, I'll have time to comment on the last lecture. There's something called the S-matrix bootstrap, where you basically write some ansatz for this extra stuff, this dot, 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 that will expand at low energies, and then you just impose all of these constraints numerically, and you try to find a solution. And there's some partial success. It's a very interesting program, but today we're just going to do effective field theory, so we're just going to expand at low energies. Okay. Yes? Sorry? The numerator is some beta, which I'll come back to. So it's just some number that has dimensions -2. Yeah.
One more thing. So one of the considerations is that you are exactly 4 dimensions.
Yes.
So you couldn't use dimensional regularization. So how would you deal with infrared or UV divergence?
Yeah, actually, okay, so we'll see that a lot of those things have to do with which logs appear in the amplitude. Everything I said actually is not in tension with dimensional regularization. We can compute loops. There's a way to go beyond tree level. Today, I'm just going to talk about kind of the analytic part of the amplitude up to some poles, right? And we'll pretend that the logs don't exist, and then we'll come back to the logs tomorrow. Okay. Okay, so in general, now this 4-point amplitude is going to be very hard to write. We just know that it has to have these poles there, but we don't know what is this extra stuff that could live here, right? So we're going to have to be content with just exploit that if we only consider energies much less than this UV scale, that is some physical scale that everything is normalized by, then I can expand my amplitude, this F, I can expand. So the leading term is going to have a 1 over lambda UV squared. So there's some like F0. And in principle, there could be like terms to any power. Actually, this one will be absent, but we're just going to have an inverse 1 over lambda UV expansion. So we'll only be able to describe the low energy physics of this. But that's what effective field theory is about. Okay? It's exploiting this hierarchy of scales to write the low energy answer. Okay. So if we do that, it turns out that the only thing that we can add here is just a polynomial. It's something which is fully analytic. It's a polynomial in S, T, and U, because we don't have any other states in this theory. We just have this scalar and this graviton, and I've assumed that everything else is at lambda UV. So if I'm expanding below that scale, and that's everything I have at low energies, then this will just give me some polynomial. Okay. Now, I lied to you here because there's also logs of this lambda UV. We'll talk a lot about those tomorrow, but for today, we'll pretend that there's no logs. Okay, so let's look at each one of these pieces one by one. So let's focus first on this guy, and let's just check factorization. So unitarity tells us that, okay, we have these poles that are dictated by locality. If I go on the pole, the residue should be fixed in terms of these lower point amplitudes that we drew here. Okay, so let's look at this one first. So I'm going to take the limit when S goes to m squared of this amplitude. And the claim is that this thing will be 1 over S minus m squared times, what did we say? This amplitude 1, 2 minus some p here will be minus p because everything is outgoing times 3 plus 4. And we've written those amplitudes, right? We just wrote, where is it? I guess I erased it. But this is the thing that we wrote as x squared. Okay, so let me write this. So this one here will just be some reference spinner 1, 2 over reference 2. This is a different reference for this amplitude 4, 3. And there's this kappa prime squared. Okay, and now I'm going to make my life easier. So I'm going to erase, I'm going to make some choice for these spinners. So I'm going to choose this reference spinner to be 3, just because I can choose anything. I'm going to choose it to be 3. And I'm going to choose this one to be 2. Oh, there was a square here, everywhere. Okay, and now I'm going to use momentum conservation. I'm going to write 4 as minus p1, minus p2, minus p3. But because p2 and p3, they're contracted against these massless guys, then I will get 0. So actually, I can replace for free 4 by 1 by momentum conservation, and just using this kind of massless Weyl equation, the fact that these are solutions to the free spinner equation. Okay, so what do I get? I get that in this limit, the amplitude is 1 over s minus m squared. And the numerator is going to be 2, 1, 3 to the 4th. And the denominator is angle 2, 3 times square 2, 3 squared, which is t squared. And I have kappa prime squared. And now let's do the same thing up there. So if I just take the limit in that function s, right? So when s minus m squared goes to 0, because of this relation, u minus m squared is just minus t, right? So u minus m squared when s equals m squared is the same as minus t when s equals m squared. So on the other hand, we have that just from the formula we wrote above, the answer has to be minus beta s minus m squared, and precisely this. Okay, so as long as we choose beta to be minus kappa squared, then this satisfies unitarity. And actually, the pole part doesn't require a new coefficient. Okay? So here, we're just writing down the answer. It seems that we need to introduce some free coefficient, but it turns out that that coefficient is just what already appeared in the 3-point amplitude. So actually, it's fixed.
So just a technical thing.
Yeah.
About how you use this blob. So
Yeah.
is it a loop? Sorry,
No. This is just like an amplitude. Yeah.
This holds at tree level.
Yeah. All of this is at tree level because it's the kind of, I'm just focusing on the analytic part of the amplitude that doesn't have any logs. And we'll talk about logs tomorrow. Okay, more questions? Yes.
Does the renormalizability of the theory change like if the theory is renormalizable, that expansion will be having 1 lambda over UV, I was expecting the answer not to depend on the...
So the only thing that changes is whether the first term is independent of lambda UV or not, right? When I expand this, if this was a renormalizable theory, the first term in this low energy expansion of this function, instead of having a 1 over lambda UV squared, would go like lambda UV to the 0. So if I take lambda UV to infinity, then I would get something left over, which is my renormalizable theory, right? So yeah, we could talk about, in the usual language of effective field theory, there's this kind of marginal interactions and relevant and irrelevant, and it's just at which power of lambda UV these things appear. But here we're just trying to write out the answer, so that's why I didn't phrase things in that language. Okay, how much time do I have? Okay, I think we are good. Okay, so now there's an exercise, because I don't have time. Work out what happens when t goes to 0. So when t goes to 0, I'm going to have two things that look like this. So I'm going to have to glue the 3 graviton amplitude with the scalar amplitude. So there will be a sum over 2 terms. Let me not write all the indices. But the important thing is that here, the helicity will be minus plus on each one of these 3-point amplitudes. And here will be plus minus because I have to sum over all possible options. So the exercise is to check that indeed the amplitude in this limit goes like 1 over t to 1, 3 to the 4th s minus m squared. And then kappa, kappa prime, where kappa was the coefficient of the 3 graviton interaction, and kappa prime is the one that appeared here. And actually, we learned something. We learned that kappa prime has to be the same as kappa. So there's no new free coupling in the interaction of a massive scalar with a graviton. It's actually the same interaction as the graviton with itself. And what is that? What do we call that? The equivalence principle, exactly. So typically, this is phrased in terms of some gauge symmetry and all of that. Here it emerges as just some pure consistency condition. Okay? We didn't have to impose anything, just locality, unitarity. Right? Gauge invariance is some device that we need to introduce when we want to write a local Lagrangian, which is manifestly local and Lorentz invariant. But these things are basically in tension with unitarity. And we see directly in the amplitude that if we just impose all of these consistency conditions, we learn that there's only one way to have this, which is if gravitational coupling is universal. So again, I don't need to invoke gauge symmetry for that. Okay, another exercise along the same lines. Okay, so the exercise showed that there's actually 2 different 3-gluon amplitudes. One is something like this, which we can write as FABC 1, 2 to the 4th, 2, 3, 3, 1. And this thing has to be antisymmetric so that the amplitude is both symmetric. Another one is this one. So this is a regular 3-point Yang-Mills interaction. Usually we call this a structure constant. This is the trace F-cubed interaction. So you can see that the dimension is higher because we have more of these guys in the denominator. So this has to have more inverse powers of lambda UV. So this is kind of this exotic like 3-gluon interaction that you can have in the standard model effective theory. This has to be symmetric to have full Bose symmetry. And the check that you have to do is that if you impose 4-point factorization, that this implies the Jacobi identity. So F A B E, F E C D. And there's a similar relation when I replace F by D, one of these F's by D, which is satisfied by this symmetric structure constant, which is also just follows from, again, imposing consistent factorization at 4 points. Okay? So we learn again that all of these business of gauge symmetry, we learned that there's some Lie algebra behind this somehow, but it just follows from these basic principles. Okay, and I claim that all group theory relations that you would find that follow from the gauge symmetry, you will find just as a matter of imposing these consistency conditions. Okay, so I don't need to invoke this from the get-go. It just comes out. Yeah?
Does the G prime need to be dimension?
This is dimension full. Yeah, right. Yeah,
But the
so.
G no.
No, the G is dimensionless. So this is actually marginal coupling, right? And so let's see why. So this amplitude has to have dimension 1 because it's a 3-point amplitude. And then here we have that each one of these angle brackets has dimensions of energy. So we have 3 in the numerator, 2 in the denominator. This already has dimension 1, right? Now this thing has dimension 3 in energy, right? So this has to have a 1 over lambda UV squared. So this is a dimension 6 operator in the usual language. Okay, so if each one of these free couplings that we find when we write these things will be an independent operator in the usual language, modulo field redefinitions and gauge invariance and all of that. Okay, and let me just make a quick comment. What about the polynomial part? So back to this gravity and amplitude. I didn't tell you what this polynomial is, but if you impose this symmetry, you can see that this F as U, there's the part with the poles that we just described, and then the only thing that you can write is some G4 lambda UV to the 8 plus G6T, or S plus U. Well, let me just write it as T, lambda UV to the 10, G7, dot, dot. And then if you go back to your Lagrangians, then you will find that this is some operator that looks like phi squared r squared. This is something that looks like phi squared dr squared. These things looks like phi r dr all squared. And you might be confused by the fact that, okay, here we have some Riemann tensor. There's many indices, but I claim that there's only one independent such operator after you mode out by field redefinitions and gauge symmetry and integration by parts. So that's the advantage of using these amplitudes, that we're just writing down the answer. We don't need to do any of this work, finding which are the independent index contractions. We just have to write a polynomial in the Mendelssohn variables, and that's completely equivalent. So that's why EFT is just fancy dimensional analysis. This is it. Okay, so let me write it explicitly. So amplitudes already mod out by both total derivatives or integration by parts at the level of the Lagrangian. And this just follows from momentum conservation in the amplitude. So momentum conservation, something like S plus T plus U equals 0. It's completely equivalent to just considering operators modulo integration by parts. So as long as we make sure that our amplitude conserves momentum, we don't need to worry about that. And also field relations, or usually imposing the equations of motion, which is how we track which field definitions we can use to get rid of certain terms in a Lagrangian. This is completely equivalent to the on-shell conditions. Things like p squared equals m squared for some external particle. It's just imposing the equations of motion, and we know that we only care about operators up to the equations of motion, which means up to field redefinition. Okay, so we didn't have to do any of that work because all of this is automatic in the amplitude. Any questions? Yeah.
So any combination of the Mendelssohn variables are going to correspond to some specific.
That's right. Yeah, you can always reconstruct which operator each one of these terms comes from. Yeah.
Also, this is exact result, right? Here we are ignoring quantum effects, the log.
No, here we're also ignoring logs. I'm just writing a polynomial because I'm writing. Yeah, this is exact, right? But by writing this polynomial, I'm just assuming that this function doesn't have any branch cuts, which is not true. And we'll talk tomorrow about those contributions. Yeah.
But if I like assume that the log terms, I'm going to change my unitary conditions.
No, they won't change the factorization, right? Like we discussed last time that the poles, they're fixed by these lower point processes, right? The discontinuity across the logs, right? Like the imaginary part coming from some particular logarithm, that's fixed by another process, which is where we compute like a two-particle cut that we have to glue. Yeah, yeah. So we can like check those things separately and enforce those things separately by focusing on different singularities in the amplitude. So this is by coming close to, yeah, when S goes m squared, if you had particle production, then you could have, okay, when S goes to 4m squared, then I know that I would have a log, and then its coefficient would be fixed by some other amplitudes. Okay, more questions, yeah. Yes, so you can compute form factors, but form factors are partially off-shell, which means that you actually have to choose an operator, and you can play similar games. Typically, form factor, what it means is that you have an off-shell momenta somewhere in the game, and you need to keep track of it, but it's very similar, yeah. Yeah, we'll talk very briefly about form factors tomorrow. Okay, more questions? Okay, yeah, that should be enough. Okay, so let me just write the answer for 4 gravitons, because if you've never seen the 3-graviton vertex, you should look it up. It's pretty scary, but the 4-graviton vertex is even scarier. But actually, the 4-graviton amplitude is very simple. So here's a 4-graviton amplitude. I'll just write the answer, and then you can try to check that you can completely bootstrap it from just this 3-point amplitude that we already wrote. So the answer is going to be 2, 3 to the 4th, 1, 4 to the 4th. So I chose this particular helicity, minus, minus, plus, plus. And then this function here will just be kappa squared over STU plus alpha squared SU over T plus G4 plus G5T plus dot, dot, dot. So this came from the usual Riemann-Hilbert, just Einstein gravity. This was the coefficient that we found for R cubed. So there's actually 2 independent poles here because we have this R cubed amplitude. This thing is basically R to the 4th. This thing is D squared R to the 4th, et cetera, et cetera. Okay. So you can check that factorization is satisfied because I already gave you the 3-point amplitude, both this one and this one. Okay, so the last thing I want to say today is, so now the strategy to classify the most general amplitude is clear. We just need to write the most general expression in terms of these angled brackets, maybe multiply by some in these Mandelstam's, and then impose factorization, which is fixed by unitarity, and then we're done. We have like the EFT expansion of any amplitude that we want. Now, it can get a bit tricky because there can be multiple such structures. So here we were lucky that there was only one such structure, but sometimes it's a bit more complicated. So I'm just going to very briefly tell you some tricks. And actually, these tricks have been used to great effect. There's a paper that I can point you to where people classified, actually one person, Stefano De Angelis, so a friend of mine, he classified all dimension 6 and dimension 8 operators in the Sennenmohr EFT using these kind of tricks, okay, just by himself. Dimension 6 had been known for a while, but dimension 8 actually was a new result. Okay, so if I look at, let me give you an example. Let me look at the O minus amplitude of vectors, so maybe gluons. In this case, we actually have many options in the menu, right? Because I could write 1, 2 to the 4th, 3, 4, sorry, squared, 3, 4 squared, but I could also write 1, 2, 2, 3, 4, 4, 1, and basically 1, 2, all these different permutations. So actually, we want some way to quickly see how many of these are independent, because we had this Schouten identity, momentum conservation, these kind of things. Actually, for this, there's a very useful graphical notation. So let me just put all particles on a circle. 1, 2, 3, 4, right? And say I have, for instance, this amplitude, 1, 2, 2, 3, 3, 4, 4, 1. So I can write each one of these angle brackets just as a directed edge between these points. So this term would correspond to square. Okay, let's do another one. One, two, three, four. So for instance, I can write this one. So this is going to be 1, 2, 2, 4, 4, 3, 3, 1. Okay. If I had other things, this is not for vectors, but say I had also some square brackets, say I had like 3, 4, 4, 1, right? I could also write other edges with a different color. So there's always some nice little graph like this that encodes any such expression. And this is useful because some of these constraints, like this Schouten identity or momentum conservation, now they become some simple graphical rule. Okay, so what was our Schouten identity? It was something like 1, 2, 3, 4, plus 1, 3, 4, 2, plus 1, 4, 2, 3. So this is Schouten in 2, 3, 4, contracted with 1, equals 0. So let's just write each one of these terms. Okay, so this is 1, 2, 3, 4. This is 1, 3, 4, 2. And this is 1, 4, 2, 3. So basically, this tells us that we can eliminate one of this. And let's eliminate the non-planar one. So the answer, if we just want to classify all of these amplitudes, the independence one, they're just going to correspond to the planar graphs. Okay? Because this Schouten identity, I can always use to eliminate these crossings. Okay? So let's just write the 3 independent ones. And that will be the last thing I do. Okay, so I can go 1, 2, 3, 4. And then if I want to do something else, which is not the same, okay, switching the direction of this is just a minus sign. So it doesn't count. So the other thing that I can do is to put multiple edges. Right? So this thing will be 1, 2, 2, 3, 3, 4, 4, 1. This one will be 1, 2 squared, 3, 4 squared. And then the other one I can do is 2, 3 squared. And then 1, 4 squared. Okay, so then I would have to take each one of these guys, dress it with a polynomial, maybe with some poles in the Mandelstam's, impose factorization. So it will be a slightly more complicated exercise, but the same program works. And you can try it. And in fact, as I mentioned, this has been done, and people have used it to classify basically all operators in the standard model EFT up to some certain dimension. Okay, so I think that's everything I want to say for today. So today we focus on this kind of meromorphic or rational part of the amplitude, some polynomial plus some poles which are fixed by factorization. I pretended that there's no logs. Tomorrow we'll talk about the logs. We'll see why they're bad and why actually they're not that bad after all. And we can understand them. And this will lead to the notion of RG and matching and many other things. Okay, I think that's it. If there are any questions. Yeah. Yeah. Yeah, it's just a visual aid. Yeah. Yeah.
Do you have a graph for when you are dealing with fractions?
With fractions? No, but a fraction I can always turn into something by multiplying and dividing by something that carries the weight, right? So that's what we usually do. We just write polynomials in these brackets, and then whatever is in the denominator I can write in terms of STU, except at 3 points, but at higher points, this is what we do. Yeah. And of course, this becomes more and more important if you're trying to classify higher point operators, because the number of these structures explodes, just like the number of operators in your Lagrangian. But here, at least, we don't have to deal with Euler definitions and gauge symmetry and all of these kind of things. Integration by parts. Yes?
I don't really understand on this blackboard where you have like the yellow square brackets. Why
Yeah.
are they square brackets?
Yeah, it's just that this is the notation that I can use to denote any expression that contains both angles and squares. So here I was focusing on angles because I just had minus helicity particles, right? But now if I mix up some positive helicity, then I would also have to have some square brackets. I can still denote it with this graphical notation. It's just that now I need 2 types of edges that correspond to both the angle and the square. And the extra ingredient, and I'll leave that as an exercise, is, okay, apart from Schouten, which has this simple graphical rule, there's also momentum conservation. So the exercise is work out the graphical rule for momentum conservation. So for instance, at 4 points, momentum conservation is 1, 3, 3, 4 equals minus 1, 2, 2, 4. So there's some graphical rule that corresponds to this, where I swap some vertices, and then if you use that, you can also classify, for instance, all amplitudes that have 3 minus and 1 plus.